Hi, we're now in part 5 of this ArcNLET training video. So I hope after viewing part 1 to part 4, you already have a good understanding of what ArcNLET was developed for and how to run it. So now I want to give you an overview of the conceptual, mathematical, and computational model of ArcNLET v3 so that you can better prepare your real-world application, because real-world applications are always more challenging than the Lakeshore example we had. And the understanding of those conceptual model, mathematical, and the computational model may help you to better prepare for your real-world modeling. So we're going to talk about essentially the conceptual, mathematical, and the computational models for groundwater flow module, and for the transport module, and also for the load estimation module. We also going to talk about some details, such as how to determine C0, Min, and Z using the transport modules. So now let's start from the groundwater flow module. So you have seen this in last video. We have run this module together. So, but now I tell you why we designed the groundwater module that way. So essentially, when we run any transport simulation, we need to know groundwater flow, so where water flows. And this module is to determine groundwater flow. That means the magnitude and direction, specifically from a septic tank to a nearby water body. So to do so, we have something to use in hydrogeology that called the Darcy's law. And keep in mind that in real world, everything is 3D. So we have a velocity in the x direction, y direction, and z direction. So what we're gonna do is we're gonna first calculate something called a Darcy velocity, which is a q here. And then divide this Darcy velocity by porosity. Porosity is how much pore space you have in a soil volume or rock volume. And this will give us this so-called a seepage velocity. This is actually the actual velocity water particles travel in pore space. And for Darcy's law, this qx, Darcy velocity, is calculated by this equation minus k partial h over partial x. So here h is hydraulic head, which is essentially where the water level is in the piezometer or in observation well. And the x, y, z are just location or coordinates. Then we can calculate the velocity in x, y, z directions. So in a standard groundwater modeling, what you're gonna do is in these two steps. So first, you solve a groundwater flow model by using MTModFlow, for example, or any software can do the job to determine hydraulic head h at every location. And then you use this Darcy's law to determine the velocity. That means determine hydraulic head first and then determine the velocity. But groundwater modeler have done this for decades, at least 5 decades, since 1970s. But you would need a you need a master degree in hydrogeology to run ModFlow. And in addition, you would need a number of data to set up something called a boundary condition. But since many ArcNLET users do not have this master degree or the data to support a ModFlow model, so we say we ask ourselves a question: can we simplify the calculation to get the velocity? And then by doing so, we need some simplification. So we need two simplification. The first one is called Dupuy assumption. This has been used for people for about 2 centuries actually. Dupuy is a French, the name of a French scientist, and he introduced this assumption. So essentially, what this does is, as I mentioned, everything is 3D. But by using this assumption, we can simplify a 3D flow into a 2D flow. So this is a sandbox experiment we did before to illustrate this Dupuy assumption. So this is a 3D sandbox. and then we put a die at different location at different depths of different locations, and we have a groundwater flow, and those are sands filled in the sandbox. We have groundwater flow from right to the left, and here we create an artificial lake. It could be also a stream, and you can see the flow path. The flow path is essentially pretty much horizontal, except near the lake there is a vertical flow here. So Dubuis said, well, this location may not be that big, and we can assume the groundwater flow is horizontal. That means we do not need to worry about this vertical variation of hydraulic head. So that means hydraulic head at each depths are the same. By doing that, this vertical flow would be 0 because head at different depths is 0. There will be no vertical flow. And then we only need to simulate groundwater flow in the x and the y coordinates. This is first assumption to convert 3D to a 2D flow. And then we need to figure out how to get this h. I mentioned before, normally we solve groundwater flow model, but now we say we're gonna use another simplification, which is also widely used in hydrogeology. That means the water table is a subdued replica of topography. So essentially that means if a process, let's go to next step. So this is the second assumption. We say water table is right here, and land surface is here, so topography. This assumption says the water table is a subdued replica of topography. That means they're similar, although not the same. And then we say, based on this assumption, we can process, or like smoothing. Well, that's what we did here. We smooth the land surface, and then we can get the shape of the water table. So be careful here. We get the shape only because here we only need to calculate the partial derivative. We really do not need to know the head h value. We just need to know the difference between h. So then we say we process the topography, and then we got the shape water table, and then we use the shape water table to calculate our groundwater velocity. So here there's another thing I should have mentioned. By Dubuis assumption, we said the hydraulic head in the vertical direction is a constant, right? And then at water table has a very special feature. That means pressure is 0. It's just gauge pressure. It's not 0 actually. It's just atmospheric pressure. And then if this gauge pressure is 0, that means hydraulic head is the same as elevation, as right here. And then we can replace h, that's hydraulic head, by the elevation. So right here, h replaced by z. But this z is not land surface. This z is actually the elevation of water table. And then we can say by processing the topography or DEM, we can get a shape water table. That means there is only a constant, a difference between the process DEM and the water table is a constant, so we can use this one without any problem. So by doing this, with these two simplifications, we do not need to solve for groundwater flow model. You don't need to run model flow. You don't need to get a master degree to run model flow. You just run ArcGIS or ArcNLET. You can get the velocity. So that's essentially the conceptual model we have. So based on this conceptual model, we're gonna need a number of input files. Number one, we're gonna have a topography data that always a DEM. This is a raster file. And then we need a smoothing factor and also a size of the moving window smoothing to smooth DEM to get the shape of water table. And then we need hydraulic conductivity, which is right here. This is K called hydraulic conductivity, and the porosity, which is the theta here. So here we assume that K is not a function of direction. We call it isotropic. So that means K value is the same in all the directions, which is fine for surface superficial aquifer. And theta you can both K and theta you can get from Circle database. We're gonna talk that more later on. And then you need essentially this item 1 to 3 is to calculate velocity, Vx and Vy in the horizontal plane, and the water body location is to ask the calculation to stop. So once you think about a particle, it move to water body, which is stop because that's not groundwater anymore. This is what we have, and so here we explain why a little bit more about smoothing and why we use raster file for DEM and hydraulic connectivity and the porosity. So you probably know raster file from ArcGIS. You have an image, you discretize it into a block. So this is a very typical in numerical modeling. So we always convert a continuous problem into a discrete problem. For example, the velocity. We're not calculating velocity everywhere for every x, y. Instead, we calculate velocity for each raster block. And so based on this raster file, we can do smoothing for DEM. So we use a moving window, and the window size we always prefer 7 by 7, but we give the option for users to use a different different window size. But again, we actually never use anything other than 7 by 7. So now let's go to the ArcNLET and to just refresh your memory. So here's a DEM in the raster file, hydraulic connectivity and porosity, and then water body and the smoothing factor. That means smoothing factor means you smooth it for 50 times. We're going to talk about this later on. So that means it just simply means you smooth it 50 times and use a window of 7 by 7 blocks. And we have these two things, fill sync and the Z factor. Those are just for, it's not for theory, it's just for operational purpose. Let's see what those are. And for this fill sync, this is essentially to avoid the situation that your flow paths will be trapped at the sink. So you can imagine if there is a sink and you have a water particle, and theoretically speaking, the particle should move out of the sink, and then to move to the next low location. But when we use this particle tracking, we cannot. Sometime the water particle is trapped in the sink, so we have to fill the sink so that water particle can move out. Most of the time you don't need it, except only where in Florida it's pretty flat. But sometimes you have this, maybe you have some valley, then you want to use this fill sync option. And the Z factor is essentially to convert between a horizontal units and vertical units. When we say horizontal units, that's related to here. Let's go back to this DEM unit, and DEM has a unit. Well, if you download DEM, you probably have a unit of meter, but sometimes you have unit of feet. That's a horizontal, right? And then sometimes you use a vertical. I cannot think of a circumstance for now. But if you say your vertical unit, a length unit is, for example, foot, then you need this converting factor to convert foot to meter or meter to foot. But most of the time, you just put a 1. That's fine. That means you are using a consistent unit of the DEM length unit. That's it. And one thing I need to also to mention that if you use a meter for DEM, everything should be meter. For example, hydraulic connectivity has a unit of length per time, and then the length has to be a meter. And porosity has no unit, so don't worry. But everything else, volume later on, would have a volume unit of cubic meter. So that's something you need to pay attention. So that's essentially all the functions within this groundwater flow module. And then let's move to So now we're going to talk about the unit of time and about the steady state model using ArcNLET. There are two things to pay attention. One is that the default time unit is day, and the other one is that the ArcNLET simulation it assumes steady state flow system and transport system. So the reason we assume steady state is that very often ArcNLET users do not have data to support a transient state simulation. Transient state means it varies with time, but steady state means everything is the same every day for the unit we're using. Of course, using steady state is not physical because nothing is steady state in real world. But if you don't have data to support a steady state simulation, the only way you can go is to assume system is steady state. For example, you have a river and you know the river stage change every day, but you may not have data to support it. And then you need a hydraulic groundwater head data to calibrate your flow model, and hydraulic head change every minute. But you don't have data you don't have data of transient data, so you have to assume steady state, right? And the other reason of assuming steady state is because of computational cost. For a steady state simulation, you assume everything is the same every day, but for transient state simulation, you have to simulate everything for a day and then for every day. That's going to take a lot of computational time and space for storing data. And so if you have in your ArcNLET and you need a specified time unit or pay attention to the time unit at several places. One place is hydraulic connectivity, right? So you have the unit of length for DM, and then you use this unit for everything of length unit. We have a part 13 talk about in detail how to make sure the units are consistent, but here I just talk about where you should pay attention to the time unit. So here, hydraulic connectivity, the unit of hydraulic connectivity involves time because the unit is length per time, right? So here you would say per day. And then another place is the decay coefficient. So here is 1 over time, right? So you have to use use a unit of 1 per day. And also min has a mass per day. You have used a unit of day. If you sometime people talk about the assumption of steady state, whether it's valid or not. As I mentioned, it's not the best way. It's approximation of system. You assume system is steady state, and sometimes people say maybe we can use it for dry season and wet season, and then calibrate the model using different smoothing factor, for example. That's definitely doable, but we have not got the chance to test it. Essentially, it's doable, but how accurate to do so, how accurate the results are, we don't know yet. If you do not like steady state at all, and you want a transient simulation, do not use ArcNLET. You can use Modflow or MT3DMS. There are many software can do a transient state simulation. And then this is a summary. So we have a two simplification based on Dupuy assumption and based on the assumption that our table is a subdued replica of topography. And because of Dupuy assumption, we are not running a full 3D model. We're running a 2D model. We're gonna talk about that more in the transport module, and the simulation is steady state, not transient state. So now we come to the particle tracking module. Let's go back to ArcNLET. This is particle tracking. So you already saw for magnitude and the direction of velocity, then you're gonna use it to track particle from septic tank to water body, and you will need a porosity to get the velocity right? And here we have three more options, three more parameters. One is water body raster resolution, and step size, and the maximum steps. So those are for particle tracking. And so this water body raster resolution is to convert the water body polygon file into a raster file. So why do we need a conversion? So essentially, you imagine you have a particle. And I'm going to talk about step size, right? So you have a particle, and now you know at the septic tank, and you know where it flows, right? And then you want to track this particle toward a body. You just move it for step by step. You say, first I move 10 meter at my first step, and then another 10 meter, another 10 meter, following the flow direction, right? And then you say, I don't want to try more than 1000 because I believe all my particle from any septic tank should already terminated within 1000 steps. That's essentially 10,000 meters, right? So this is not a big deal. You just want to put a large number there. But once a particle reach a water body, it should stop. But how are you gonna know it reached water body? So again, you come to raster, come to the raster file. You say if a particle move 10 meter at a step size, it's already in a raster file, a block of a water body. Then you say, then I'm done. I should stop, right? That's why you convert a polygon water body file into a raster water body file, and this resolution is for the purpose of this conversion. And we choose a half size. We say for the DM we're using is 10 meter resolution, and we say, well, we should probably have a finer resolution for the water body so that the water body would not miss a small river or would not pass a small river or stream. So this is by default is a half size of the DM resolution, and then that's all you need to know about this particle tracking. Let's see if anything else I missed. The particle water body raster resolution, step size, and maximum step size. That's it. And so here I want to talk a little bit more about ArcNLET. So here you see we have this T button. This is T essentially for particle tracking. It is a tool we developed. It's not necessary. You don't need to run it. We develop it as just a tool. Again, you need to run groundwater flow, and this name is just the task name you want, whatever you want to use. And then the magnitude of groundwater flow you calculated, and also direction in the groundwater flow module. And the same thing, water body, porosity, water body resolution, step size, and maximum step. And here XY. So in the ArcNLET particle tracking, the particles are put automatically or by default at each location, each septic tank location. But here, you have the flexibility to put a particle anywhere. Let's say you are wondering, you say here, well, I want to develop a new house, and then where the water gonna move from the new septic tank to the water body, right? You can then you put a look XY coordinates for that new location, and it gonna tells you where the water gonna move. But this is just a tool available to you, and you don't need to use it for your ArcNLET simulation. Now let's move to the transport. We're gonna talk about again the conceptual, mathematical, and the computational model behind this transport module. And this is could be pretty complicated thing. Look at this. This is our conceptual model of our transport module. As I mentioned before, our flow model is 2D, just in the XY coordinates. And as a result, our transport model has to be 2D. So that means we simulate the plume in the XY plane. But in order to calculate mass, you need 3D, because mass is defined by a mass in a volume, right? And then you have to have this Z so you can have a volume, right? So what we did is we choose this EPA Bell-Clair model. This is used by EPA. So what it does is like this. So you have a let's say drain field of your septic tank, right? And so this is the width of the dream field, and then you have the length of the dream field, but this is not perfect for width and length, but assume this is the width of dream field, this is the length of dream field. And then the nitrogen gonna move from dream field to the water body, to the water table, and enter the aquifer, right? So we're not simulating actually the movement from dream field or at the water table. Instead, we're not simulating from this horizontal plane. Instead, we have this vertical plane, and this vertical plane is our source. This is, you can imagine, this is equivalent to the source from the dream field, right? And then the y is the width of the dream field, and the z is the we call it, this is imaginary. We have more discussion there, but this is z is simply to convert or expand a 2D plume into a 3D plume. Then we can use it to calculate the mass to the aquifer and to the surface water body, right? So now we know what the y and z's are, and now let's talk about C0. C0 is essentially the mass or the concentration on this vertical plane, right? So go back to ArcNLET to link you to the ArcNLET. So you see here, let me choose that one here. So this is y and z, and this is C0, right? And these are three locations related to our conceptual model. So now we have this conceptual model. We know it's a 2D flow we're simulating, and then we expand it into 3D by using this imaginary depth z. And then we're gonna see, okay, so even it's 2D flow, how we gonna calculate the plume from this plane into this aquifer, right? We normally solve, let's say for a 3D problem, we have this so-called advection dispersion equation. So this term is advection, v is the velocity you calculated a moment ago in the groundwater flow module. So the concentration, I say here there's a source plane. This vertical plane, the source plane, and water moving from, say, left to right, right? And all the contaminants, this is a source plane, right? So this, imagine this is a plane that producing nitrogen continuously at a concentration of C0, and then this concentration or mass gonna move with water, with the groundwater flow, and also it disperse out. So this is illustration what it means disperse out, because it's not a pencil flow. It's the contaminant will not move along a line. Instead, they're going to spread out because of this is porous media. You have a mechanism called a dispersion here, right? And the amount of dispersion is actually governed by the parameter here we call dispersivity. And we have essentially three dispersivity. One is we call longitudinal dispersivity. That means it's going to disperse out along flow direction. And we have this so-called a transverse, and we have a horizontal transverse. This is a bird view of the plume. It's not a vertical cross section. So we have a horizontal transverse is spread out, and that's alpha th, and t is the transverse, h is horizontal. If it's 3D, we have a vertical transverse, that's alpha tv. But in our case, we're only simulating 2D flow, and we need a longitudinal dispersivity and horizontal transverse dispersivity. So that related to here, dispersivities alpha L longitudinal, alpha th is a horizontal transverse dispersivities right here. And then after this, we also need to consider, we already have V that has been taken care of from flow model, we don't worry about it. But here, we're gonna consider something called a denitrification. We use this word very often in the past, but essentially what it does is, let's say, maximize it. You have nitrate, and you have organic carbon, you have bacteria, and they're gonna use them to produce energy, and just like people use meat to get energy, and the bacteria use nitrate to get energy, and then nitrate becomes nitrogen gas, organic carbon become carbon dioxide. You have water generated, right? So this process, most of the time, people use a first order kinetic. So a change of concentration with time is a function of concentration with a factor k. So k, we call it decay in the model, but it's actually it's a denaturfication rate. It's at the unit of 1 over t, right? So we have analytical solution. That's the work of Domenico and Robin. They say the concentration, if you have a source plane like this with concentration C0 at the source plane, and then you're going to spread out, and the concentration at any x, y, z and time t will be at this function, right? And again, we're doing steady state flow and 2D flow. So your transport has to be in steady state and has to be in 2D. I'm sorry, flow transport do not have to be steady state, but that's our choice. You can have a steady state flow, but transient state transport, but that's our choice because safety tank is in the field, is in operation for many years. It's not just a new installation. That's why you choose to have a steady state transport simulation. So if it's steady state, you just say t is infinity. You're gonna reach steady state when time is long enough, and you're gonna get rid of z, so you get this no z anymore. So now let's go back. So we already know what these dispersivities are, and what we know this denaturfication decay. That's small k in the equation. And now let's look at C0. So this C0 is the concentration at the source plane, right? So the C0, first of all, what's a unit? So the unit of C0, that's concentration of nitrate. And if you read literature, people always report in the unit of milligram per liter, and this is a liter. And we say we're going to use it directly. So this is the value you see here. For example, 40 means 40 milligram per cubic. I'm sorry, 40 milligram per liter, right? But I mentioned to you before, we use a meter as our length unit, right? So you need to convert from liter to meter. That's why you need a converter, volume convert factor, right? So 1 cubic meter is 1,000 liter. That's why you have 1,000 here. So this explains things here. So let's go back. So we now know what those conversion factor, volume conversion factor, and unit of C0. So this is C0. You can use whatever unit you want, but this is what people commonly report in the literature. So we use milligram per liter. You can use gram per liter. That's not a big deal. You can use gram per cubic meter. That's not a big deal. But if you use cubic meter, the converting factor will be 1. And then question, where to put and how to determine C0, right? We have we make it a little bit flexible, but also make it complicated. So here you can put C0 here. That means here you're gonna assume 40. You're gonna assume C0 is 40 for every septic tank uniformly, right? But you don't have to. You say, well, there are many septic tanks, and the concentrations are different. You may heard a dog bark, so I'm working in my office. My office neighbor has a dog in his office, and so that's not my dog. So you have you use a 40 here, and you assume it's a 40 milligram per liter for every septic tank. That's fine. But if you say I have different value for different septic tank, then how are you gonna do it? So you're gonna prepare your septic tank file to input that information. Look at this attribute table. So this is a attribute table of a septic tank file I'm using. So those information is really actually not relevant. I just got it from FDP, and those are locations and street address. That's not used for the modeling. But we add a attribute table at the end and we call it N0 CO and C. This is not NO, this is N0. So then here you have 40, which is the same everywhere. But if you have, if you know um, the concentration of individual septic tank, you can input it here. You say, for example, here, you know, this is probably a house with, say, 10 members in this household, and then they produce more nitrogen. You can put 400. That's not a big deal at all. So this gives you flexibility to input information you have for different septic tanks. Once you have that, let's look at, this is 40, right? But if you use a septic tank, where is it here? If you use a septic tank, because I already have a 40 there, I will not use this 40, right? So, or whatever value here. Then we put a -1, indicating that the C0 is not inputted by you, but it was inputted by the C0 in the attribute table, the last column of attribute table in this file. So this just gave you a warning sign. You don't need to input a C0. Okay, so yeah, and also again, if this is for not using Vismod, right? We have another module called Vismod. If you use Vismod, and things actually be simplified, or you can say it's be more complicated. So Vismod gonna simulate the concentration of ammonium and nitrate at water table. So that means you do need to worry about it. You don't need to worry about C0 at the water table, but you will need to specify the initial concentration beneath the drain field, and that's essentially above the water table. And then Vismod gonna take that concentration of ammonium and nitrate beneath water table, and then run a simulation in the Vido zone and automatically calculate the C0 at water table. And then you're gonna use that information for your groundwater flow simulation. So we're gonna talk about that later on. So this is how we're gonna input and determine C0. But if you say I have nothing, I don't use Vismod, and then you have to go to the literature to get C0, or you can go to field and measures C0 there. Okay, now we go to more options of this transport module. So here, if you look at this, oh, by the way, here we talked last time. So Domenico and Robin solution for steady state, SS, and 2D. And this, if you choose this option, you do need to consider the denitrification. So you see here, this window, this option just inactivated. But if you choose the decay, which is always the case, and this you need to input this parameter, right? And here we have more options. One is a plume warping. Let's talk about that. So what's warping mean? So you have a plume, and when you use a Domenico and Robin solution, which is here actually, and it simulates the plume along a straight line of flow. But you have seen that before. The flow direction is not straight line. Look at here. There's some curve here, and then we need consider that curved flow path for the plume calculation. So what we did is using a function built in ArcGIS called warping. So here, this is what Domenico Robin solution gave, and this is a straight line of the flow. And then if the flow path is actually curved, you're gonna warp this flow along this curve. And what we did is we put those points as a control points or controlling points, and then there is a linear algebra to do it, and there's three ways to do it. One use spline, polynomial 1, and a polynomial 2, and you can see that here. Remember the points we put along the plume, and those are points set here. So we use a 48 control point per cell for warping, and we have a spline, polynomial 2, and polynomial 1. And they used to work, but spline this is actually the best option we have. and it used to work, but unfortunately, after one upgrade of ArcGIS, this doesn't work anymore. We have not get a chance to correct it because there's so many things, and we're always lack of resources to do so. But polynomial 1 and polynomial 2 works, and polynomial 2 is actually better than polynomial 1 because it's more advanced methodology, and so we always choose polynomial 1, and it never give us any problem. And you use warping, approximate warping right here. And then another one, this one is a threshold value. So what threshold means? Remember, this is a numerical calculation. It can give you some number really, really small. It could be, here we use 10 to minus 6 um, uh, milligram per liter. The computer can give you something like 10 to minus 20, 10 to minus 30. Those are meaningless, right? We don't want to keep those numbers in our calculation. We say if the calculated concentration of nitrate or ammonium is less than 10 to minus 6, which is truncated to 0, which should not be a problem at all. This is the threshold. If you want something bigger, it's up to you. You can choose any value you want. And then post-processing. What post-processing does? I'll give you some example. So here. So this is the warped plume from one septic tank, and this is water body, right? So if you do not do a post-processing, your plume gonna look like this. It gonna just, it's a plume. It just terminate right here, right? But this doesn't looks very realistic. And then you probably cut it here and put it here, and to make it more meaningful or intuitive to you. And this change is not that big, right? But sometimes it's important. Say, here's a case. Let's say you have a very small stream, and this is a river. So if you do not do a post-processing, this is no post-processing, not it's not here too. What happened is this model or the software or the code will not see this river. You're gonna go move through this river. Well, this doesn't happen all the time. It just depends. This stream is really, really small. Remember, we use the resolution small, but the stream is smaller than the resolution we have, and they're gonna pass the stream and reach to this river, which is um, you're gonna give more load for this water body, but less load for this water body, right? So what we're gonna do is we're gonna cut it out. This is our final. So medium and full. There's two way of do post processing, and then you're gonna stop at this water body. You will not reach to this water body, right? And so let's go back to the software. So it's right here. So right here. So post processing none. That means you don't do anything. And the medium and full. So full is really time consuming. So most of the time, if it's large scale simulation, means you have thousands of septic tank, I would suggest you to start with none. And if you have say a couple hundred septic tank, you probably would start with medium. But full, full is better, but you're gonna take more time to run it. From the load estimation perspective, if you use none, it probably will not make a big difference because you have a high here, a low there, it may cancel out. But use medium at the starting point, that'd be fine. And then we have one more thing here. This is a plume cell size resolution. And so this is, remember we had this talk, we talk about the right here. We talk about the raster, right? So we're gonna calculate concentration in this case for each raster block, right? And if you have this resolution too high, you're gonna lose detail of the plume. But you have the resolution too low. I'm sorry, if the resolution too high, too low, you're gonna lose the spatial variability. If it's too low, too high, you're gonna require a lot of computational resources, which is also not desired. So you're gonna choose a good one. So here I'm sorry, we made an so here we use a 0.4. 0.4 is 1/15th of the y value. Let's say if it's 6, it's 0.4, right? So you use 12, and this become 0.8. It's just a 115. There's no theory behind it. This is just rule of thumb. We use it and it works, and so we just keep using it. And you can change it. You can change to say zero point 0.5. It's fine. It's not a big deal. It's just automatically set as 1/10 of this y value, right? Okay, so this is almost done except one thing, and it's very sophisticated thing. That's about the mean and the z value, right? So let's talk about that. So okay, here z value. Okay, so here. Okay, here. So the z value is really needed for the load estimation, and let me tell you why. So here is a conceptual model we use for load estimation. So you have this groundwater aquifer, for example, and then you have nitrogen from septic tanks. And then during the aquifer, this is in, we call in. This is a mass inflow to the aquifer. And during aquifer, you have this denitrification process. Bacteria eats nitrogen as energy source, and then you have this denitrification, right? And then whatever left would be the load to surface water body, because everything ends at surface water body, right? So load is what we want, and denitrification is calculated during the transport simulation. So here's how we did it. So this K is the decay coefficient, and the C is the concentration, and the V is the volume of each raster block. We have index of I, and the phi is the porosity. This is how we calculate amount of denitrification, simply because we use first order kinetic. So if we use a zero order kinetic, this equation will be changed, but we use first order kinetic, right? So this MDN has been taken care of during the transport simulation, right? But let's see how to calculate min. And the calculation of min, we didn't write it in the user manual or technical manual. Instead, we explain it in a paper we published. And this is Li Wang is my postdoc. Fernando is my student. So we work together, and those are people who helped us. And Rick Hicks was our project manager at DEP that time. Polly is a close colleague, and Rob is another student. So we explain this in this paper. So if you're interested, you can read the paper, but I will explain in this manual, and the paper is available right here. Let's see how we do it. So in theory, so now I'm trying to convert you into a master of hydrogeology. So this is a source plane, and this is equivalent to the drain field. You just think in that way, in simple way. And then the contaminants or nitrogen or nitrate come into the groundwater by two mechanisms. It go with water, that's called advection, and also disperse out, because Fick's law is based on the concentration difference. Concentration here is higher, concentration here is lower, so it's just disperse out. So this is how we do the calculation. So this part is advection, this part is dispersion, right? And you see here, V we already taken care of in the flow model, and alpha is the parameter you dispersivity along the longitudinal direction, and here is a derivative with respect to x. So we have analytical solution. So we just take the analytical solution, and then we end up with this, right? So y is the width of septic tank, z is the depth. So we're gonna talk more about it. Phi is porosity, V is groundwater flow, C0 is source plane concentration, K is the decay coefficient. That's it. And then you see this equation. This is interesting. You see Z is the Z here. This is the source plane height. And min is how much mass coming into the system, right? And those two are related by one equation. That means, so if you specify min, by using this equation, we can calculate z. I'm sorry. If you specify z, by using this equation, we can calculate min. So it's just two sides of a coin. Let's go back to the software. Say here. So here we have two options. You can specify z as we do here, and then min will be calculated automatically. If you specify min, like what you do here, and then the z will be calculated automatically, right? So this min you can put a value, or you can get from the Visma simulation. So this is up to you, right? Um, this is the theory we have, and then the question is how are you gonna do for your real world modeling? Let's say, how are you gonna specify min? Min is it's unknown. Nobody know what it is, and nobody measure it, but we can estimate it. So this is how we do it. So we normally estimate min by using literature data. In this report, and this is what we did for Porcelusi, and we explain how to do it. It's in page 42 of this report. So number one, first thing you say, okay, you need to determine nitrogen release per person per day, say 4.8 kilogram per year. Well, you need the per day data because this is time it's for day, but based on this review, it gave us the amount of nitrogen per year. And then the number of number of people per house. For Salusi is 2.5 per household, and then it goes from drain field to septic tank. First from septic tank into drain field or leach field, right? We assume that during this process, 2.7 or 70% of nitrogen just disappear because there are so many processes going through in the septic tank. And okay, after that, so here's the example. So we have well, 2.4 for Salusi is average between 2.4 and 2.6. So here we have 2.4, and then I'm sorry, 8.4, and that's equivalent to 23 gram per day. And then this is similar to people use in literature. Sometimes people use 21.7, like in Ryder, who work in FDOH, but it's not big difference, right? And also, like say Anderson, who is expert working on this problem, he sometimes use 22.4, right? So, and this is his philosophy or his calculation. But so here he's using 80%, so we're using 70% based on this reference, right? So this is essentially how we do it based on literature data. And then so here you have min. So you got min from literature, and you calculate your z, right? And keep in mind this calculation for each septic tank, right? Because each septic tank may associate with its own k value, its v value, especially v value, and then you can have min, and then you have a z, the same min for say two septic tanks, but because each septic tank has a different v value, and so their z value may be different, right? So essentially you use this one to calculate z for each septic tank. But sometimes we found out that some calculated z value is too large to be reasonable, because we know the vertical transport is always limited in comparison with horizontal transport, right? So for this purpose, we put a z max here. So here's your flexibility. You say, well, I believe the nitrogen cannot be more than 3 meter. Then you put 3. And if you say it cannot be more than 1 meter in depth, you put 1. So that's your option. But we give the flexibility to you. So this is how you're going to calculate z based on min and have a restriction for z value, right? And then the other way to do it is to um, specify z and then calculate min, right? So how are we going to do it? How are we going to determine z value? So this is another tricky part. So what z value is? This is z value. Yeah, you give a z, you're going to calculate min correspondingly. So z here is actually a imaginary factor, when simplify a 2D plume into a 3D plume into 2D plume, or you extend a 2D plume in depth to a 3D plume in order to get a mass. So this is a diagram made by Pauli at DAP before he retired. This is what the plume should look like. So you have a dream field and move downward and it spread out, right? So this is 3D plume. But we're not simulating a 3D plume, and the depths are not the same, right? But we're using EPA's conceptual model, and the depths here is constant for the entire plume, right? So essentially, the Z plays a role to convert the mass of this volume into a mass of this kind of volume, right? So you can say, I have a Z, have different value in depths. I integrate out, I divide it by a C value, I got a Z. So this is essentially what Z value for. It's essentially upscaled volume or depth. I'm sorry, or height. So, but in order to do this, you need to have a CZ, means concentration at different depths. This is always impossible to have in real world application for TMDL, right? But we have a chance to work on it. So we used a case for, this is for, so I will delete this slide, this is not useful. This is a case for a Nelson site in near Duval County. And in this site is interesting because number one, they have a residential septic tank has been used since 1976, and Nelson did a detailed site characterization. He have soil cores, have rain gauge, piezometer, monitoring well, so on and so forth. And then the most important thing, well, this is the hydraulic head, and you can see this is the rainfall data for dry season, wet season, dry season, wet season. We just use from June to October as wet season. I forgot details, but we separate into dry season, wet season anyway. And then we have a head observation for this site. We have dry season, wet season. Interesting. This is near Duval County, near Jacksonville, but there's really not a big difference between different wells, and there's some difference for dry season and wet season. So this is something unrelated to Z, but I put it here anyway. So those are measured TKN concentration, ammonium concentration, and nitrate concentration at 3 depths from 3 wells. Again, so this is figure is a little bit not a little bit busy, but let me do it again. So we have 3 wells, TW1, 16, and 17, right? For each well, we have water sample from 3 depths, 1.8 meter, 3.7 meter, and 6.1 meter. So this is a unit of feet, but I use meter here. 3 wells, 3 depths, and 3 nitrogen species. TKN essentially for organic nitrogen, ammonium, and nitrate, right? So we have the measurement of concentration over depths, and then we can use this formula to estimate a Z value. Essentially, we do integration and we divide it by C prime. C prime is the maximum concentration at the shallowest location of sampling, and then we got a Z value. So here's a table. So the Z value, again, we have here we have 4 wells. So we have 4 wells. We have 3 species of nitrogen, and then for each well and each species, we can estimate the Z value. And you see there is a variability. It could vary from less than 1 meter to more than 2 meters. But roughly speaking, it's about 1 meter or 1.5 meter. So that's always, this give us some idea. So we normally always use 1 meter or 1.5 meter. We may do some adjustment later on. So this is a really long video, but I go through the conceptual, mathematical, and the computational model behind ArcNLET, and I also give some specific information. I hope this is useful, and I end up the video with this figure we generated before. This is how you can use it in the real world. You say this is a simulated plume, and this is household, and this is location of septic tank, and so this can give people a context so they can understand the model simulation in the context of, say, their neighborhood, where it goes, how high the concentration is. So with this, I will end up with this part 5 video. And then part 6, we're going to talk about Vismod, which is to run ammonium and nitrate between the drain field and the water table. And starting from there, we're going to add ammonium into ArcNLET calculation. We're going to talk more about it. Okay, I will see you in part 6 of this training video series.